Let's see, I guess you're going to introduce our first thing. Francesco. Good morning.
Good morning.
Ladies and gentlemen. Giuliano Preparata died on February 24, on April 24, in Frascati. And we felt that we had to remember him in this conference for his important contribution to Confucian. I'm just introducing this memory of Giuliano, and then I will pass the speaker to Martin Flashman. He's been in touch with him very much in the last years. Giuliano got interested in Confucian immediately after the announcement of March 1989. I like to remember a paper written by Giuliano together with Tullio Bersani and Emilio Del Giudice, called First Steps Toward an Understanding of Cold Fusion, of Cold Nuclear Fusion. The date of appearance on the Il Nuovo Cimento Note Breve is May 1989, and it was received April 26, 1989. So really, a month after the announcement of Professors Fleischmann and Pons. The important thing is to note that in this work, an important way of looking at the phenomena was pointed out, was presented, and it contained two features that in these 11 years have been more and more put in evidence. The first feature was the fact that phenomena like cold fusion in a metal lattice could take place only if the threshold in the density of absorbed deuterium in the metal was reached. And the metal was indicated in the order of 1 deuterium atom per metal atom, palladium in the case. And the second, that the outcome of the fusion reaction differed from what happens in well-known high energy D plus D fusion reactions, not be preferably neutrons or tritium or other particles, but just helium-4, and energy would be transformed in heat. So he saw the possibility of using the detection of helium-4 as the nuclear ash demonstrating confusion. And Giuliano was very active in all these years, and in particular, the second international conference on confusion was held in Como in the end of June, beginning of July 1991. And again, the three, Giuliano, the Giudice, and the Bersani, were the chairman. And I remember that conference as the most the most fruitful conference that I remember. In fact, in that conference, I want to remember two data that were presented, and they were strongly demonstrated in the years later. The evidence brought out by Mike McCooper that found that the threshold was necessary in order to obtain heat effects in his electrolysis experiment. And the evidence by Melvin Miles that helium-4 could be found and could be correlated with the heat measured. So the two things that in that paper had been foreseen were presented. As you well know, the difficult reproducibility of the system has made it not that easy to reproduce continuously. But in 11 years, which I lived intensely together with Giuliano, we have seen growing the evidence of these two facts. I want just to remember what Giuliano did at Enea. As I said, he died in Frascati. He was in Frascati because proposed in 1998 the start of a new program, and he was strong enough to convince politicians, managers of Enea and NFL to start a serious program and to have it funded by state, Italian state. And in fact, this program has been started mostly because of the push of Giuliano Preparata in Frascati. And he asked a sabbatical year from the University of Milan, where he was a professor, and went to Frascati. And he had a house in Frascati where he died. And he spent his months, last 6, 7, 8 months in Frascati, extremely active, pushing people, and it was very easy to perceive the effect of his pushing. The life in the laboratory has been changed since Giuliano was there. As I said yesterday, in February, we had a 2 days meeting of the Science Program Committee. And Giuliano was not in the best of his shape, wanted to participate, and was extremely active with his intelligent criticism, pointing out the faults of the abstracts. That was extremely helpful and helped us to make the choices for this conference. And I'm very grateful to him for his help. I don't want to take more time. I want just to remember that Giuliano was not only a passionate researcher in cold fusion, he was a great scientist in all the sense. He has been giving light in all the fields of physics and also out of physics, in biology and the rest. And it's a pity that he's not with us today. But I think that we have to remember him and to think to him as a guidance for the future of science and also for cold fusion. I think that Martin Fleischmann will take over and tell you his memories.
Ladies and gentlemen, and especially Emilia, who is with us today, I really feel quite inadequate to carry out this task. And as Franco has said, we are remembering Giuliano especially because of his contributions to the subject, which will be the theme of this meeting. But I think we should just remember that Giuliano's work initially was in nuclear and particle physics, where he confronted this extremely difficult question of why leptons are free and why quarks are confined, quarks, which are the constituents of hadrons, are confined. And of course, he sought the answer to this problem in the behavior of the quantum fluctuations, which under certain conditions form a giant coherent field, which confine the quarks and thereby explain this problem, which has puzzled people intensely, why we cannot get free quarks. I think I would say that this early work demonstrated his characteristics, that if he thought one line of argument was correct, he would insist on that line of argument, irrespective of what everybody else was trying to tell him about it and trying to persuade themselves and him that he was wrong. Now, in due course, of course, Giuliano's thoughts and Emilio del Guidice, who is with us today, turned towards ordinary matter. And there is an analogy there, because, of course, the coherent electromagnetic field establishes the ground state. And we have to think, really, we have to think about the behavior of ordinary matter also in terms of field theory. Not just, field theory is not an esoteric subject to be confined to particles and nuclear physics. It is extremely important in ordinary matter, probably most important of all in biology. And it is this particular line of reasoning which brought Giuliano and myself into contact, because I too had been thinking about this problem, and I feel it's a little difficult for me. I don't want this to, in any sense, to be a talk on matters which I have thought about, but it's somewhat inevitable that I should pay some attention to this, because this was our point of contact. And the question which I started to pose in the 1960s, the series of questions that I started to pose in the 1960s, were, is it possible to devise electrochemical experiments which demonstrate the need that we have to think about the behavior of ordinary matter in terms of quantum electrodynamics? I'll return to the slide in due course. This is important because I will just say that there were only 3 people in the world who ever realized that the work which we had done on cold fusion was probably part of a wider program of work. And 2 of these people are in the audience here today, but I won't embarrass them by naming them. Giuliano realized this immediately and questioned me closely about this. And one of the topics which came up, which is of some relevance to the work which we want to carry out in Frascati, was this good old question about the behavior of ions in solution. I have written about this on occasion now, which is interpreted, as you know, in terms of the diviable theory, where we have a central ion surrounded by an ionic atmosphere. And this model was proposed by the Triple in the 1920s, and everybody was very happy with it. I don't think Debye would have proposed this model if he had set about it in the 1960s, but everybody thinks that this is the last word of the interpretation of the thermodynamic properties of ions in solution. And of course this is not true, because if we do not have ions, static ions, surrounded by a static ionic atmosphere. Ions move, as Einstein showed us. The ions move at random, they execute Brownian motion. And if we then ask ourselves what happens if we try to make this consistent with Maxwell's equations, we realize that there has to be radiation. So in fact, we can only have this model here. This will only apply at absolute zero, which is interesting. Of course, we can't have an ionic solution at absolute zero. Well, I didn't know, I only knew one theoretical physicist who was interested in quantum field theory in the 1960s, and he said, well, it's quite obvious, you have to think about this in terms of quantum electrodynamics. I said, well, yes, but how? And I didn't know what to do about it. And I put it on one side until in due course, Giuliano and Emilio del Guidice and I started to talk about it. And they said, well, it is quite obvious that if you have a coherent electromagnetic field, you will have the solvent, which in this case is water, divided into coherent domains and incoherent domains. A model which was in a fashion very popular in the 19th century, but went out of fashion when Bernal and Fowler said you cannot have two sorts of water based on the laws of quantum mechanics, because water molecules or any salt-polar molecules are indistinguishable, so there only has to be one sort of water. Well, here's the big question. The big question, of course, is that while this is true in the framework of quantum mechanics, it is not true in the framework of quantum electrodynamics. And quantum electrodynamics tells us that this model is entirely possible. And there you are, we've had this for the whole of the last century. We know that the properties of solvents are much better interpreted in terms of a two-phase model than in terms of a one-phase model, but because Bernal and Fowler said that the one-phase model was not consistent with quantum mechanics, everybody dropped it. Well, the thing the point which we realized was that if we have coherent domains of solvent and incoherent domains of the solvent, the ions will go into the incoherent domain, where they will themselves be coherent. Now that paper is out now and does actually give a much better interpretation of the properties of electrolyte solutions than does the biological theory. I won't labor this point. The only reason I want to raise it is because our program and Frascati was in fact going to be wider, and I think I sincerely hope it will be much wider than that for cold fusion alone. And one of the topics which we intend to investigate is the effect of magnetic fields on the conductivity of ions in solution. Now, there's hardly any work now on conductance, and whenever it's like a Boston learning curve, whenever a field becomes unpopular, you can be sure that there's a great deal more to be found out. And this in fact is based on the work of Jardin. Our Russian colleagues here can maybe tell us a little bit about this in Moscow. Really, it is what I'm saying is a little back to front, because it's been realized for a long time that weak magnetic fields here, B, or weak electric fields at right angles, have an enormous influence on biological processes. And because the theoretical physicists can't think of a reason why this should be so, they say it must be wrong. Well, of course, this cannot be. I think that I'm producing some laughter in the audience, and I think that Giuliano would have liked us to take this forward view of the subject. And what is wrong about it is, of course, that some model of the world is wrong. And if we have a coherent, if the ions in solution are in a coherent domain, then they behave as though they have a much bigger mass. And of course, they can tune into much weaker magnetic fields and much weaker electric fields. And this is going to be, we hope, one of the main themes, one of the major themes not on cold fusion in Frascati. I don't think it will make us many friends. Well, let me just, there is work on the influence of strong magnetic fields, which leads to incoherent scattering. But the question of course, what happens to coherence is a very big question, which takes us into biology and physical chemistry. Chemistry in general. Now, I have often been wondered why it was that Giuliano's interpretation raised opposition. And I think it is that he said, well, all right, let's take an experiment, and instead of interpreting it in the left-hand side, classical mechanical paradigm, setting up a model and interpreting the data, let's set up a quantum electrodynamic paradigm and set up the model and see whether we get a better interpretation. The problem with that, of course, is that you can be criticized for setting up the model, and you can also be criticized for having the wrong view of quantum electrodynamics. And I think Giuliano suffered greatly from that. Because the normal view in quantum theory is that you have classical mechanical paradigm you have the quantum mechanical paradigm, and the quantum electrodynamic paradigm somehow emerges out of the quantum mechanical paradigm. Now, Giuliano and Emilio and I don't have this view. We think there's only one paradigm in nature, and that is quantum electrodynamics. Sometimes classical mechanics, adequate description, but we think that quantum mechanics may be an adequate description sometimes, but it is sort of isolated from the rest. It stands on its own. Now, Giuliano followed the route you would expect him to have followed as a mathematical physicist. He said, let's interpret nature in terms of a mathematically complete theory. I did not have such opposition in the early days, because I said, no, don't let's do that. Let's instead see whether we can falsify the existing paradigm. I'm sorry, you know, I don't give easy lecture. When I say something, it's always very difficult. You have to put up with it. Here you are. We have we have the Maxwell's equation applied to ions in solution. So we have this. We see that we cannot possibly have microscopic reversibility, because if these things radiate continuously, then the system has to go to absolute zero. So I really do rather follow the mathematics which was developed in the 20s and 30s, except from a physical point of view. I say, well, mathematical completeness is all right, but we can argue forever about that. Let's look at whether we have violations of the second law. If we have a violation of the second law, we know we have the wrong paradigm. Well, on we went, and as Giuliano asked me intensely about what I was really doing, and I told him these were very profitable conversations, because we didn't have to talk at length about things. He said, I'm doing this, and he said, yes, next topic of conversation. And we were doing pretty well looking at the effects of time and space and the effects of space-time. And of course, in the end, I realized there was a missing element. There had to be energy. Why is it that biological and chemical systems, I think physical systems also, manipulate small energy quantities so well? And the answer, of course, is that this is incomprehensible except as part of a many-body. If you think about it in the many-body problem, it becomes immediately obvious how this happens. So, in due course, Stan Pons and I said, right, we have one more shot. We are going to have a look at whether we can induce fusion processes in a lattice at low temperature. That's why we are all here. And Giuliano latched onto this, and Emilio, they both latched onto this immediately, and I can tell you that they came to Salt Lake City, and I was very busy, Pons was very busy, and I said, Giuliano, are you going to, he was going to give a talk about it. I said, Giuliano, I said, Professor Preparata, I didn't know him that well then. I said, Professor Preparata, are you going to discuss this in terms of quantum field theory? And he said, of course. So then in that case, I'll come to your lecture. And it was illuminating. My wife is here, and she said, if you ask her, she will tell you that. I said, I've met a man who says exactly what I say. Either we are both crazy, or we're both right. So, I then also said to Giuliano, well, there is this absolutely amazing experiment carried out in 1929, and which has since then been totally messed up. And that is this work of Alfred Köhn on the diffusion of protons in palladium wires. So let me just ram this down your throats. I've spoken about this before, but let me just point it out once again, because it does lead on to the work in Frascati, which Antonella Delino and Emilio De Guidice will tell us about. If you put protons in here, in the wire, and you apply an electric field across the wire, negative end here, positive end here, you find that, in fact, the protons, the hydrogen moves faster towards the negative end than towards the positive end. And here is one of Alfred Köhn's results. You find, in fact, he measured the arrival time. This is a beautiful experiment, absolutely fantastic experiment. And the great Walter Nernst congratulated Köhn. Nernst was not a person to congratulate anybody except himself. But he congratulated Alfred Köhn on the execution of this experiment. Alfred Köhn measured the arrival time of the protons of the hydrogen at the different zigzags. And he showed that, in fact, this is the classic result. He showed that the hydrogen arrived more quickly at the negative end than at the positive end, the middle line being the diffusion. If you reverse the polarity, you could actually make the hydrogen go faster towards the other end of the wire. And those results follow the Nernst-Einstein relationship. And it is really amazing. What is so amazing, I think Alfred Köhn perhaps didn't realize that this result was so amazing, because what is so amazing about this is that hydrogen is, or deuterium for that matter, is extremely strongly bound in the lattice. You can do a cycle, Born-Haber cycle. The dissolution normally of hydrogen or deuterium in the lattice is exothermic. So you know that this is the minimum binding energy of the proton or deuteron in the lattice, extremely strongly bound. So how can you have a very strongly bound hydrogen ion or deuterium ion in the lattice, while at the same time it is free to move? The answer to that is, of course, you can only interpret this in terms of quantum electrodynamics. And what Giuliano realized immediately was that there was then, therefore, a means of confining the deuterium ions in the lattice, making use the strong binding and the high mobility and the electric field to confine, and we shall hear about this during this conference, to confine the deuterium ions in the lattice in such a way, and I have actually talked about this before, you can confine the ions in such a strong way, I have the last view graph, that we can create a coherent system. Normally, you see, the behavior of ions in the lattice would not allow you to achieve very high states of charge, but because we can confine the ions with the electric field in the lattice, we can achieve a very high state of charge in the lattice, and thereby induce a high rate of nuclear fusion. And in fact, with this system, Giuliano and Emilio, initially in Milan and then subsequently also in the work in Frascati, have achieved, in a fairly routine way, specific rates of excess entropy production range 10 kilowatts per cubic centimeter, and sometimes as high as 100 kilowatts per cubic centimeter, which is higher. I think on occasion even higher than that, which is of course much higher than can be achieved with the systems which Stanford and I initially developed. Well, I just would like to say one final personal appreciation about Giuliano. For me, it would be wrong to describe him as one man in a million. I think it would be even wrong to describe him as one man in 100 million. For me, he was a man with this breadth of vision, which I think is very necessary to develop science. With this breadth of vision, he was one of these people who only occur once in a lifetime or once in several lifetimes. And I'm sure that his work will be increasingly appreciated, and I am just deeply saddened by the fact that he did not live to see that himself. So let us remember Giuliano, and let us move forward to this next phase of work in the natural sciences. And thinking about Giuliano, say, when people say that everything is known, you can be sure that nothing is known. Let's move on to the next phase.
We now begin the series of talks. These are each scheduled for 30 minutes with 5 minutes question and answer period. We'll have to keep fairly close time due to the tight schedule. The first talk will be given by Dr. Antonelli Nino. It's titled Flash from Pond's Effect in a Novel Electrolytic Configuration. And I'll give you a 5-minute warning time.
Good morning. My work, the work that I present now, was done in the last month together with Giuliano Preparata and other co-workers that you can see on the slide. The first thing to say is that 11 years after the first announcement from Fleischmann and Pons, heat excess seems a quite well assessed feature. What we have to do now is to collocate this phenomenon inside a scientific frame, more scientific frame. This is what is the main aim of our research program in Frascati. This is the summary of the talk. We will discuss briefly why our choice towards quasi one-dimensional cathodes. I mean very thin wire, a very thin and long deposited film of palladium. We will discuss briefly the peculiar feature of the loading in this kind of thin films, and I will show you the calorimetric data and conclusions. So the first reason why to use this very particular geometry that I will show in a moment is to verify the Q-Naronoff effect. The Q-Naronoff effect is the name that Giuliano Preparata given to a particular effect he described in 1995. The name was mutuated by the very famous experiment well known in quantum physics. It is the Bell-Maronoff effect. This effect the effect is the influence of the potential vector on the motion of an electron immersed in a magnetic field. What is important is that the potential vector affected the motion, the trajectory of the electrons. So Giuliano remembered this effect when he found that the electrical potential affects the motion of deuterons inside the metal. So this is the reason why he given this name, Q-Naronoff effect. I propose from now on to call it Preparata effect. So we want to verify experimentally this effect. What is the influence of the electric potential on the confinement of deuterons inside the palladium? We want to improve the experiment already done in the Leda laboratory by Giuliano Preparata and Guido del Giudice, using a new kind of design of the experiment. We were using Frascati in the past year thin films, so we decided to join our experiments to do some more complete. We want to realize an electrochemical cell prototype, very compact, easy to use, and reproducible, because we want to study physics at the end of this phenomenon. We want to study loading at high ratios. We want to see what happened to the gas loading at low temperature, to detect helium-4. It was foreseen by Giuliano Preparata in 1990 or 1989, exactly. We want to see if there are nuclear transmutation induced by the fusion of deuterons inside the metal, to look for X-ray, soft X-ray emission, and to take a picture of, using a thermal camera, a thermal picture of the strips of the palladium that we want to charge. So some things we have already done, and you can see we present several posters in this conference. I want to tell you before that I will present just a sketch, a phenomenological view of the phenomenon. On Wednesday, Emilio del Giudice will give a theoretical talk in which everything will be more clear. So this is the structure we used for our experiment. We used to call it a bastrophilic deposition. The strange name came from the ancient Greek, and it indicates the motion, the path of the hawk that moves from right to left and from top to bottom, and again from left to right, and so on. This is a sketch of the strip, our film, a very thin film, whose thickness ranges from 0.5 to 2 microns. The width of the serpentine is 50 microns, and the total length is 80 centimeters. We have several pads here that allows to measure the loading in different sections of the wire. This is a picture of a cell. As you can see, the cell is very small and compact and very easy to assemble. This one particularly is Teflon made with rubber O-ring because the cell is sealed. You can see this is the cathode and the anode, electrical contact and measure of temperature and so on. It's very, very easy and very small. The external diameter is about 8 centimeters. What is difficult to measure in this configuration is the real loading of the sample. We want to measure the loading using, as usual, the R on R0 curve, Baranowski curve, that relates the loading to the electrical resistance. But it's not easy to measure the electrical resistance of such a strip, of such a field, is very high, which has a very high resistivity when dipped in electrolyte, because the electrolyte has a conductivity itself. So we developed this kind of circuit that is based on the use of several relays that disconnect the circuits of electrolysis during the measure of the resistance. So there is no leakage of the current measure of the resistance in the electrolyte and vice versa. There is no matching between the two circuits, the circuits of electrolysis and the circuits of measure. This is what we have. This is an example of electrolytical loading of this kind of deposition. As you can see the different curves refers to different pads on the deposition, so different part of the strip. You can see that maximum loading is reached at different time for different parts of the strips. And it is very astonishing feature. As you can see, there is a strong deviation from the Baranowski curve. This is an example of loading in H2O. We expect a maximum to be at 1.8. as Baranowski, as you can see in literature, but here the maximum is strongly depressed. Nevertheless, we reach an apparent very high loading. You can see here is 1.2. What happens? How to interpret these results? The first effect is, of course, due to the presence of the electrolyte. This is the total of the previous curves. As you can see here, this thinner is the measured curve. There is a drop in the resistance when the electrolyte is put into the cell. So we can say, okay, there is an effect of, there is a parallel, an electrical parallel due to the electrolyte. So we have to normalize our curve to the resistance of the electrolyte. There is a parallel in the resistance. One resistance is due to our strips, so this is in the order of a few kiloohms, and another resistance is due to the electrolyte. We can measure, we measured, and we know that it's in the order of 10 of kiloohms, so one order of magnitude more. Nevertheless, there is a parallel. We can calculate it from this drop here, and we have a normalized curve. It's not, again, the Baranowski curve. The maximum is not 1.8, it's not the expected maximum. What happens? First of all, we know that electrolytes behaves like ohmic conductors. In strong electrolytes, molar conductivity is approximately proportional to the square root of the concentration. For very dilute solution, as in our case we use 10 to minus 4 molar solutions, the concentration can be assumed, the conductivity can be assumed linear in concentration. We observe a decrease of the peak from the maximum that can be justified only by a decrease of in the resistance of the electrolyte in the order of 100%. This is very hard to believe. In fact, we measure the conductivity after a long electrolysis, before and after a long electrolysis, and we found that there is a decrease from 107 to 94 microsiemens. So it goes in the opposite direction, and probably due to the metal-alkaline discharge during the electrolysis. So this is not reason for this behavior. We did other experiments using an example wire. This is an example of the same electrical configuration, but using the wire, 2 meters wire, long, 50 microns in diameter. In this case, the effect is less than in the previous one, but it's still there. We have the maximum here is 1.7 instead of 1.8. It's an interesting feature that during deloading, the maximum reaches an higher value. Then the wire is breaks, it's usually. If we try to do a gas loading of the deposition in 1 bar of deuterium, this is deuterium in this case, we obtain this maximum here. It's not true. Again, we are lower than the Baranowski curve. Again, if we put the same sample in the electrolytical cell, we see there is a very quick crossing over a maximum, but the maximum is very small. So if you switch off the current, there is a deload. This feature here means that we have really reached the right side of the Baranowski curve. So we are really in a region of very high loading, but we are not able to give a qualitative explanation to this behavior. But looking in literature, we found that it's well known that there is a thickness dependence of the critical solution temperature of hydrogen in palladium films. There is a decrease of critical, as being measured by Gris and Metal, and this paper here, I can give you the reference. It was measured a decrease in the critical temperature of thin films compared to the bulk. This corresponds to a shift of the maximum of the Baranowski curves towards lower concentration. You can see here in this graph. This is the relative increase of the resistance for a bulk sample in this case for 550 angstrom fields. Was found that the isotherms evolves with a number of cycles of absorption, desorption. The first things that came to mind is an effect dimensional effect due to the electronic property of the medium, but the electronic property of the medium went to a stationary state after a few hundred angstroms. We are talking about 1,000 angstroms of sample, so it must be some other things. Gleason proposed in 1983 an explanation based on the presence of defect in stress, mechanical stress inside the sample. Probably there is a change in the distribution of the site energy inside the lattice due to dislocation to defect into the crystal. If there are many defects into the crystal because of the procedure of deposition of the crystal or metallurgical reason, octahedral site can be depressed in number. So there are less octahedral site available for deuterons. So this has an immediate effect on the chemical potential of deuterons, of the electrons inside inside the metal. Here I want to show you two chemical potential curves that are obtained starting from the principle of coherence in condensed matter. Details can be found in the book of Giuliano Preparata of 1995 and in the doctoral thesis that I can give you if someone is interested. But it was calculated, the chemical potential curve for the beta phase and the gamma phase, a new phase that starts to enucleate after when the beta phase is complete. So as you can see here, the beta phase chemical potential curve is lower than the gamma phase, and there is a crossing occurring at 0.65. This corresponds to the maximum of Baranowski curves. This is the point when it starts to enucleate a new phase, a gamma phase, in fact. So what happens is that the reduction of the potential wells in the octahedral sites and then shallowing has the effect to increase the potential, the chemical potential of the electron in this way. So what you see is that the crossing to the gamma phase chemical potential curves occurs at lower concentration. The effect is to decrease the concentration, so the gamma phase starts to enucleate to lower concentration. This moves the maximum of the Baranowski curves towards lower concentration. Is what we saw in literature. It is what we saw in our experiment. So what happens? This is the old famous Baranowski curves. If it starts to enucleate a new phase at a lower concentration, let's say, I don't know, 0.5. It depends. This is just a qualitative sketch. We didn't have the number to put inside our frame yet. We hope to do better in next month. But if we, in this point, we leave the Baranowski curves such this. Then we are again on the Baranowski curves at the other side. So the system tunnels to Baranowski curves, because in this region here we have again a phase coexistence between beta and gamma phase. This is very similar to what we see in our measurements. There is something similar in literature as well. This is another typical curves obtained in literature. Here you can see the increase of the relative increase of the resistance in thin films. In this case, very, very thin film. This is 120 angstrom films. This is the the value, this one, the lower curve, is the value at room temperature, and the others at very, very low temperature. This is because it's very critical to work with this kind of films, because they tend to be stripped from the substrate during cycle of loading and deloading cycles. They are very delicate, they are not robust structures. So you can see, this is very similar to the sketch I showed you before on the Baranowski curves. But on Thursday, Emilio Del Giudice will give you a more complete view of this phenomenon. But this is qualitatively the reason why we think that we are really loading these structures at very high loading. And this is a reproducible effect. I can show you 10 and 10 curves such as the one I showed you before. Now, we came to our calorimetric data. We use static cells to do this experiment. The cells are the one I showed you in the picture, in the photograph at the beginning of the talk. We have measured heat excess in the order of 1 or 2 kilowatts per cubic centimeter. This figure corresponds to a very small quantity of heat because the sample is very, very small. The volume of the deposition is 25 × 10⁻⁶ cubic centimeters. So the neat heat excess is in the order of 30-50 milliwatts. That corresponds sometimes to 50% of the input power. Usually the experiment stops because the deposition is breaks. We have several problems in our measurement. We reach the reproducibility when we overcome critical concentration, but the overloading of a sample affects its lifetime. Most of the experiment stops because of the breaking of the cathode. And this breaking is due to the velocity of the loading or to the tentative of deload samples. So it strips off from the substrate. Another effect we saw is that at the beginning we start to use with UV hardening raising transparent cells. They are transparent to the infrared. So when the sample starts to increase its temperature, the radiative part of the contribution to the heat dissipation, the radiative part of the radiative contribution to the heat dissipation becomes important and deviates from the calorimetry. So the calorimetry is quite critical. This is an example of a typical experiment. In the first graph, you can see that this pink curve here is the relative increase of the resistance, and the red curve here is the output power compared to the input power. This is the percentage on the right scale. As you can see, as soon as the sample reaches high loading value, it starts the production of heat excess. And in this case, particular case here, we have up to 30% of the input power. It's very clearly measured. Another important thing to say is the different thermal regime that we saw in black cells compared to the white cells. For black cells, I mean cells in which the cathode is palladium film, and the white cells is a cell in which the cathode is a gold film, using the same electrolyte. We saw a different thermal regime. Here I show you two different experiments in which you can see this curve here are the input power. The scale is the same in time, and it's the same input power, more or less. Here is the response of the temperature. This is the behavior of the temperature inside the cell compared to the reference external temperature. You can see here that even if the input power is quite the same, the response of the system is qualitatively different. This is a very noisy signal. This is a very smooth signal. What does it mean? It means It means that the thermodynamic regime of our cells is not in a stationary condition during all the experiment. It's impossible. If there is some heat production inside the cell, there is a change in the thermodynamic regime. So, by definition, it's impossible that our cells works in a stationary condition. So, we decided, we discovered at the end, that the isoparabolic calorimetry is the only reliable method to measure heat excess in this kind of cells. Isoparabolic calorimetry consists in supply small amounts of power at definite time interval and to measure the consequent variation of temperature. This allows you to follow eventually change in the thermodynamic regime of your cell. So we decided to add this kind of analysis to our cell in the future. Then the conclusion. So we are ready to perform a complete experiment. We hope so. We would like to have three types of calorimetry together: linear calorimetry as usual, isoparabolic calorimetry, and calorimetry based on the counts of number of helium-4 atoms. There is 1 helium-4 atoms per fusion. So it should be very nice to have a count of the number of fusion that happens inside the sample. What is left to do is to do a direct measure of the PD temperature using a thermal camera to have a map of the distribution of heat. We want also to measure the non-thermal energy output. There are X-rays, soft X-rays produced by the sample. They are produced by the relaxation of the atom that have interact with the electromagnetic field generated by the fusion, the 24 MeV electromagnetic field. These soft X-rays can generate pH change in the electrolyte because of the photodissociation. We would like to perform experiment in Raman spectroscopy to detect the presence of metastable states eventually induced by X-rays. We want to look for transmutation on the PD nuclei that are due to the interaction of these strong electromagnetic fields in the first 10 to the minus 24 seconds after the formation of an excited helium-4 atoms after the fusion. And these last two items we want to do together with Professor Lee.
We have time for a few questions.
Very interesting system of experimental you have presented.
Could you turn that on?
I'm interested in the very crucial experiment that can be done. It's very important when you load where the neutrons are going. Deuterons. The loading is where the hydrogen of neutrons are going.
Where are they going?
And there are techniques now that you can see at atomistic scale, like what is called scanning tunneling microscope.
Scanning microscope, I don't know, but it is possible to see the occupation. So it's possible to see the occupation of deuterons inside the lattice using high energy flux X-ray spectroscopy.
Right.
As example, or neutron spectroscopy. But neutron spectroscopy is difficult because of the dimension of the sample. You do not have enough sample to do neutron spectroscopy.
No, but I think they don't give the information which is desirable, that it usually can tell by. So on the surface effect, you can see where they are located, because it's crucial for the distribution. You know about that. And another comment.
We do a limited time limit on person. Can we move on?
And, the use of the neutron spectroscopy and the high energy X-rays, that's a well-known way to locate the neutrons. But I think an interesting question that's related to the use of SEMs is the idea of doing a post-mortem, that is to look at your electrodes afterwards. In particular, the Baranowski curves and the business about loading, the standard folklore about that is that as you achieve greater ordering, and when you go into the beta phase, the resistivity goes down. And it would be very interesting to see the damage in your wires and to understand if it's tied to residual loss of periodic order, and in other words, to really understand what's going on.
Yeah, which kind of damages? Because the wire is completely stripped off, the substrate is completely curly.
Right.
So it's not
Yeah,
easy.
no, I know. I understand it's hard because there's small samples, among other things. But looking at them before and afterwards might be an interesting, actually it might be fruitless. I don't know. You might learn something.
Takes two more questions.
You mentioned measuring helium-4 in your last transparency. Do you intend to measure helium-3 when you don't have all the problems and worries about contamination of helium-4 from the atmosphere? Do you intend to measure helium-3?
Yes, but probably after we get measured helium-4. Before, the first thing to do is to measure without any doubt the presence of helium-4. Technically speaking, it's possible to measure helium-3 as well.
Do I understand correctly that you turn off the electrolytic current during the time that you're measuring the resistivity?
Just to check in which part of the Baranowski curve we are.
Yes, I understand. How long a time is that turned off?
I can show you the graph again.
The reason I ask...
Enough to reach a maximum of the Baranowski curves.
Well, the reason I ask, if you turn off the current to these thin films, they deload very, very rapidly. And the consequence of that is that not only don't you have the composition you had initially, but you also have a composition gradient, which will impact on resistivity. And so it's very difficult, I would suggest, for you to relate the resistivity to the composition under those conditions.
Due to the time, we have to move on. Thank you again very much. Our next speaker will be Dr. Jacobs.
Hi. See, when time came to do abstracts, I submitted an abstract on fast ion emission because I had some recent results that were very interesting. I presented a paper on this at the APS in March and subsequently did some work. In the meantime, I generalized these results, and Mike McCouvery and others encouraged me to talk about the generalization here. So I'll be talking about fast ion emission, but I'm also going to broaden the scope of the presentation. I hope this will meet with your approval. I'll be talking about theory ideas. This is a purely theoretical presentation, and my theory is addressed ultimately to the issue of low-level neutron emission, the Kasagi three-body experimental results from the accelerator. It refers also to fast ion emission of the sort seen by Chambers and Cecil. It's applicable to the Wolf anomaly, radioactivity observed in electrolysis, and it's also relevant to heat production and helium production, tritium production in cells. It's a rather ambitious program. What I'd like to do is start with a brief introduction, and as it turns out, a brief history lesson. Those of you who've sat through my ICCF talks before recognize that I have yet to get any of my messages across because my talks are either too complicated or too mathematical, so I'm going to make a big attempt to try to get a simpler version of the talk in the hopes that it will be more understandable. Fusion was first observed in the fusion between deuterons was first observed in the 1930s, and a naive billiard ball picture of the collision. This is my attempt at being understandable. It's like this: a deuteron coming in one side, deuteron coming in the other side. They hit, they touch, they go off 3 and 1, and 1 and 3 in the different combinations that are possible. Now, microscopically, there's spin quantum numbers and angular momentum quantum numbers. Basic idea is neutrons and protons each have spins. In the deuteron, the spins add up together. In the tritium and helium, the exclusion principle means that 2 protons have to have alternate spins, and a neutron can have a different spin in helium-3, and so forth. Now, if you're going to put together a theory for deuteron-deuteron fusion, you'd like to take that into account. Moreover, if you're going to have a theory of deuteron-deuteron fusion in a lattice, you'd probably like to take that into account as well. In addition, there's angular momentum. Most of you probably remember is the issue that gave you a headache way back when you're forced to study. The basic idea is if 2 deuterons come towards each other and hit each other, if they classically hit head-on, there's no angular momentum. But if they were to miss slightly, it's like they're chasing their tail, and that has angular momentum associated with it. So this would have no angular momentum. This would have angular momentum. Now, it turns out you'd probably like angular momentum to be conserved. That's a good thing, and the quantum description conserves angular momentum. So you'd like also to do it quantum mechanically, because this is microscopic scale. These are microscopic particles. Quantum, of course, applies. And all of these thoughts and discussions that I'm saying mirrored the thoughts and discussions that went on among the physicists of the time, the 1930s and 1940s. Now, the basic formulation of the problem, is there a pointer handy? If not, I'll just try to find it. My finger, my pointer, yes. The initial modeling of this fusion process involved an initial state wave function that had 2 deuterons and then a wave function describing the distance between the 2 deuterons. This guy. Now, the 2 deuterons have 4 coordinates. Some of the coordinates are internal and some of the coordinates are relative, and this is very important in the initial theoretical description. The final state, you have, for example, the tritium and perhaps the distance between the tritium and the proton being modeled over here. And so the basic problem that was faced was how to determine initial states and final states consistent with quantum mechanics and the reactions and get it to work with experiments together. Again, here's the history. Schiff, writing from my home university, MIT, was the first to talk about the quantum mechanics involved in the theory of DD fusion. And what Schiff said is if the nuclear interaction were scalar, which basically means if it's like hard spheres, then spin would be conserved and angular momentum would be conserved. And he wrote out the rules and the laws for it. A little bit later on, Lerici and Schwinger got a model for the deuteron that they put together, and in order to get a even first order description of the deuteron, they found that they needed a tensor interaction for the strong force. This was known earlier, postulated earlier by numerous other theorists. The first serious paper taking advantage of tensor force, tensor nature of the interaction was Konopinski and Teller in 1948. And their basic argument was that, well, you want to conserve total angular momentum, And they worked out the laws for the various channels, incoming different angular momentum, total angular momentum, spin, what would happen on the outflow. Now the issue is when the first experiments were done, at low energy, you would have expected in the center of mass frame, the collisions would be spherically symmetric. And in fact, what was observed is they were non-symmetric. There was more reaction going forward and coming back and less reaction squirting out the side. And that amazed the theorists of their day. And it turns out Konopinski and Teller figured out the hows and the whys by going through this argument, looking at the different channels and observing that S waves coming in with spherical symmetry penetrated, and the P waves with dipole symmetry penetrated a little bit less, but still penetrated even at low energy. That was the origin of the asymmetry that was observed. A shrewd observation back in days when the nuclear forces weren't known properly, and the experience of the community in modeling such reactions was quite limited. The first major advance in the modeling, rigorous modeling of these reactions, was made by Wheeler in 1937. And what Wheeler basically said was, you have nuclear states, which perhaps you know, these guys, and then you have the channel separation factors, which you're trying to solve for, those guys. And what Wheeler did is said, let's find out what the formulas are for the channel separation functions. And it's basically pretty straightforward to plug solution into the Schrodinger equation, use variational principle, and get coupled equations for the channel functions. And this method is called Wheeler called this the resonating group method. The resonating group method was used for the first computations of the DD fusion cross-section. Wheeler also did an angular reduction of his resonating group method equations into channels that conserved total angular momentum. And he got coupled, thank you, he got coupled channel equations written down. So in 1937, you have the formulation of resonating group method, which establishes a useful mathematical basis from which to calculate the DD fusion cross-section. Now, strictly speaking, if you're going to get a cold fusion theory and you want it to apply to fusion in the lattice, you'd like it to be consistent with what was done earlier, with the normal DD fusion mechanism. You'd like it to at least reduce down to what normally happens. More papers, these guys actually used a resonating group method for the first serious calculation of the DD fusion cross-section. Unfortunately, back in those days, the strong force wasn't known particularly well. In the meantime, Mata, Johnson, Reed, Yale, other nuclear potentials were fitted up from scattering data. Boersma, in 1969, published the results of a PhD thesis where he used the good nuclear potentials as the basis for a resonating group method calculation of cross-section, and it's greatly improved agreement between theory and experiment. Present status of all of this, which actually Jerry Hale talked to us about in Hawaii some years back. The resonating group method, in fact, is still in use. You find papers in the 1970s and 1980s published. You also have the R matrix, which was introduced by Lane and Robson in the 1960s. The basic idea, so you have a wave function which has the same basis states and channel functions, but you fix them and then you vary the amount of each of these solutions that you put in. And when you put them in, you get an algebraic equation for the channel amplitudes, which is a standard R matrix method. The application of the R matrix method from atomic physics and chemical physics to nuclear physics happened relatively late, but these days many people do R matrix methods as well. The two methods are not completely independent. In fact, you can use the resonating group method as a basis for generating states for the R matrix method. In fact, some authors in the literature will look at a calculation. One will call it resonating group method, and the other will call it R matrix method. Now, once again, you would like whatever theory you're going to propose for cold fusion to be consistent with what's known from previous physics. What I'd like to do now is examine this in a little bit more detail, hoping to move towards coupling the nuclear and the lattice physics together in a self-consistent fashion. For example, there are many solid state theories which are very good. There's a nuclear theory which is very good. We'd really love to put them together to get the best of both possible worlds in order to have a good overall theory for working with cold fusion type reactions. In the two-body version of the reaction, two deuterons, you've got a Hamiltonian that's got 4 particles and 4 sets of particle coordinates. You're trying to solve this problem. Now, initial state solution might look something like this, with 4 terms. One of them has internal coordinates for one nucleus, internal coordinates for another nucleus, separation describing what happens as they come together or go apart, and another factor for overall center of mass. So you have 4 coordinates and 3 types. 2 relative internal nuclear coordinates, a relative coordinate, and a center of mass coordinate. Now, this separation between the types of coordinates gives you the key to coupling between the nuclear microscopic and the lattice macroscopic degrees of freedom. If you put the deuterons in the lattice and you look at what the coordinates are now, you get a slightly different version of them. You still have 4 coordinates. You still have 2 internal nuclear coordinates. But your relative coordinate now is determined by the lattice physics or by the kinetics rather than by the two-body physics that you had before. So if you are interested in hooking up the nuclear fusion problem to the lattice problem, these 2 coordinates are what you need to pay attention to. So in fact, your wave function that you had before for the free particle system now gets turned into something that looks like this, which has 2 nuclear wave functions now hooked up to a lattice wave function. And the lattice wave function has the center of mass and the relative particle coordinates as variables in the lattice wave function. And what this does is this provides the connection between the nuclear problem and the solid state problem. And this gives us the key now to provide us with a rigorous theory of how to treat these things. This leads immediately to a generalization of the resonating group method. What we do is we say Ansatz wave function is made up of the nuclear part, which might include 2 deuterons, might include a proton and triton, might include a helium-3 or neutron, or might also include a helium-4 nucleus. And then a second part, which is the lattice wave function, which knows about the center of mass and knows about the relative coordinates. The Ansatz wave function mirrors what was done by Wheeler in the resonating group method perfectly. The channel wave functions are replaced by the lattice wave functions. And Shazama, you have the lattice resonating group method. And this provides an adequate starting place for cold fusion calculations. This allows you to put the best physics you possibly can for the nucleus and the best physics that you possibly can for the lattice, put them together in the same problem. And I represent this as a good starting place for our calculations. I also would like to point out that the R matrix method from microscopic nuclear physics can be generalized in exactly the same way. We start out with a channel, nuclear channels, lattice channels that are fixed, and amplitudes. And variational principle gives you a matrix method. You have a lattice version of the R matrix method. And this can be used to give some results. And the results are very interesting. Now, having a theory, we're interested in applying the theory. And in order to apply the theory, we need to understand how the coupling between the macroscopic and the microscopic works. The lattice system can vibrate. The vibrations are quantized. And the quantization of the problem gives you phonons. Within the context of phonon theory here, position operators now are functions of the lattice amplitudes, many of them. Each lattice phonon amplitude obeys a simple harmonic oscillator problem. To couple the lattice now to the nucleus, you work with either the lattice resonating group method or the lattice R matrix method, and it gives you naturally the coupling precisely, rigorously from first principles in every case. For example, if you were to take your nuclear potential to be the 1-pion exchange potential, which is a term that appears in some of the fancier models, it's good first starting point for the nuclear interaction, you get an ugly looking expression. The expression is a function of the separation between the nucleons. So R. It's the distance between a neutron and a proton, for example. Now, the relative separation between the nucleons, in the limit that the neutron and proton are part of the same deuteron, that's an internal nuclear coordinate, so there's no coupling to the phonons. But if one of the neutrons and one of the protons, if one of the neutrons is in one deuteron, one of the protons is in another deuteron, then the distance between those two nucleons is now a function of where the nucleons are relative to the center of mass, but also a function of how far apart the deuterons are, which makes an explicit functional lattice coordinates. So we now have a rigorous way to couple lattice and microscopic and macroscopic degrees of freedom together. In order to get that coupling, you take this expression and you stuff it into this OPEP or Hamada-Johnson or Reed potential, anything that you like. You turn the crank and out comes a very high order nonlinear mess, but it's the right mess, and it describes the strongly nonlinear coupling between the nucleus and the lattice. Now, the resulting theory, when you put it together, is frightening. You have channel lattice wave functions that are functions of a very large number of coordinates. And then you have a very nonlinear coupling between the large number of coordinates. Now, strictly speaking, when I saw this in 1989, I got frightened. This is, of course, frightening. In order to do anything with the theory, you have to have a physical picture that allows simplification. Now, such a simplification exists. We know that in the limit that all the modes are incoherent and thermal, that this theory gives rise to no new physics. The only way that you can get new physics out of it is to have one or more strongly excited lattice modes that talk to the microscopic modes. So the simplest picture that you can work with is one where you have a lattice wave function that has one highly excited mode. That gives you the simplest problem. This problem was discussed in a PhilMag P article I published, one of my few publications in this area. And the basic idea is that you can separate the local degrees of freedom from the macroscopic degree of freedom by making a position coordinate, which includes the highly excited phonon mode explicitly, and all of the other phonon modes are included as a local coordinate. This gives you a very clean way of treating the effect of all the modes and focusing on the importance of each of the modes and the way it comes into the problem.
1 minute.
So, if you include the phonon field into the problem, you get a new set of multi-channel equations. The phonon mode is included, and you have the lattice channels now associated with each of the reactants and each of the different degrees of the phonon field. You can also develop a version of this, including angular momentum conservation. And what you find is the phonons can contribute angular momentum to the microscopic nuclear degrees of freedom. And this is interesting. So, we'll run out of time before I get to the end of the applications, but the basic idea is that you can show pretty quickly that direct conversion of fusion energy to the lattice in a direct reaction doesn't work. All reactions then have to be at least second order. The second order reaction, which is the simplest one and the first one you'd analyze, is the null reaction, where you have a fusion process at one site and a dissociation process at the other site that are energy balanced. If you take this problem and you analyze it using the theory I just described, you get a two-site ansatz wave function you get a second-order coupling between the sites. This, again, derived rigorously. The essential character of this equation looks like this in the limit that you modeled the interaction between the deuterons in a radial lattice potential. What's new is there's a kernel here. And what it says is when the deuterons get close together, they can come together to form helium. At another site, a helium breaks apart. When the helium breaks apart to become deuterium, it breaks apart at the origin. So this gives rise to a source of the origin. You can solve it, and you get this. This is done for molecular deuterium potential. You find when the coupling is weak, you get a small injection of probability near the origin. If you have many bodies, many sites working together, the coupling is stronger. You get a bigger effect, and you get neutrons at low levels. You have more sites involved, you get a bigger effect with neutrons at high levels. And if you, at some point, this can keep going up, and you can actually calculate an overlap probability consistent with Kasagi, the Kasagi three-body reaction. So a naive picture of Kasagi would have a deuteron coming in and hitting two deuterons close together, which is described by this model. But this will give lots of neutrons. Professor Kasagi, last time I checked, earlier today, was still alive. We have a live professor problem. Now it turns out that if the interaction with the lattice contributes angular momentum, the angular momentum gives rise to a centripetal barrier which restricts the outflow of the neutrons. And it only takes 20 to 25 quanta of angular momentum, corresponding to 20 to 25 phonons injected, to shut off the neutron and helium-3, the tritium and proton channels, so this becomes clean. And Kasagi's results can come from this, and the numbers hold together. To defer to the session chair, who's about to come over and strangle me and throw me out the window, I will put my conclusion slide on. More applications involve fast ion emission and heat and so forth. The theories now exist for the different processes, and the numbers at this point are within the realm of what the experiments are reproducing. Many of them have been talked about in previous presentations.
Can you explain why protons with nuclei react? Thank you. Can you explain why protons with nucleons react in picometer distance within megaseconds? As for instance the theory of Professor Lee shows in PhysRefC February issue of this year. Can you get these numbers reproduced from your models?
See, time-dependent formulation of this model follows directly from a superposition over states. Each of the states follows the physics that I described here. So all such problems are resolved essentially trivially through doing time-dependent summations. So we can systematically address each and every such conundrum.
Going back to your nuclear physics part, deuterium program can be now solved exactly as a forwarded program. You don't need resonating loop or matrix approach anymore. This is new development happening. But one question I have to you is, in your input you have one-ion exchange potential, but nowhere mention of Coulomb repulsion between protons and protons. Is that included in the input, or you put in later?
I gave the OPAD potential as something I could write down as an example to show how the coupling between the microscopic and macroscopic degrees of freedom worked. The same procedure can be applied to any potential, including three-body potentials systematically, as well as Coulomb potential.
But my objection would be, why not include the Coulomb potential equally as a one-time potential?
The Coulomb potential is assumed to be included equally in this part. I didn't write it down, and I didn't present all my view graphs that would show that, but it obviously is part of the interaction. It's included on an equal footing. I'm not suggesting at all that it be ignored. Of course
not. Peter, I want to congratulate you. I think you made this as clear as is humanly possible in 30 minutes. I have one question of a practical nature. Are you at a point now where you can predict or define the real-world environment in which this operates?
The basic formulation, a machine to turn a crank on and grind out answers systematically, in my view, is now available. There are something in the neighborhood of 7 or 8 problems which are worked. Your request for your particular problem, which is the one we would like to do, has not been completed yet. Although I do have estimates now that in fact show that the Kasagi range is consistent now with what can be done in the systems that are the experimental systems. The heat numbers are consistent with what it is that's available. The thing that the experimentalists are going to have to figure out how to tell me to make an apple-to-apple kind of comparison is, this is tough. Which collection of photon nodes are you excited? How much are you excited? If we can work out a theory for input stimulus to phonon excitation, then we can have first principles predictive capability at the level that you're hoping for, and I'm hoping for as well.
We'll get 2 more questions. We'll get these 2.
Your sophisticated calculation make me mad or reasonless. I can't understand what you made calculation. Sometimes sophisticated calculation makes 10 to 8 orders of magnitude mistakes. And please explain in plain word why you can eject 21 million electron volt alphas from the solid with a summer energy of 25 milli electron volt. In plain word, please.
The picture is being worth a
No,
thousand
please
plain
picture.
words.
Please by common word.
This is the basic issue is that we said that all the interactions that are of interest have to be second order. Second order in this case means that you have a fusion interaction at one site. You have a fusion interaction at one site which couples to the lattice in the way that I just described. The phonon mode couples to an alpha particle in a nucleus. In the case that the nucleus happens to be palladium, there's a dipole coupling. That coupling can eject the alpha particle with a rate that can be calculated and which has been calculated. And in light of the model here gives, at the end of the day, numbers which are consistent with the observed reaction rates. So the particle type, particle energy, and reaction rate estimate is consistent with the NRO measurements in palladium deuteride. And the application of the model to titanium deuteride, as done by Ed Cecil, gives a spectrum of particles and the energies in agreement, general agreement, rather precise agreement with the products that Cecil measures.
We have not much time.
No,
Very
I know,
fast.
I know.
Very fast.
It's nice to see actually that we're beginning to talk the same language. I would suggest though that you don't need the second order process if you do matching throughout space. What I mean by that is, in a truly exact formulation of the problem, you have scattering everywhere, and you don't just have the bulk boundary condition associated with a periodic lattice that you've used. Now, the comment with regard to this is that, actually it's a question. Have you considered?
Is there a question?
Yes. Have you considered how you might formulate the problem in terms of including actual effects at surfaces and going beyond the current formulation?
Let's see, in response to your first point, you and I can settle our remaining differences the way scientists normally do it. Usually pistols at 20 paces.
No, I'm just talking.
With respect to your second question as
let me make the comment about that. I will be talking about that, but it boils down to a different form of coherence. Implicit in what you said is a nice coherent interaction, but there are other ones, such as the entire solid coiling at once.
But as must be obvious, the formulation I proposed allows the specification of any surface description of the lattice that you like.
But that requires matching. Have you considered the matching?
Matching or not matching, but formalism is general enough to allow any description you'd like to put in.
Solid-state physicists haven't solved that problem except by matching, and it's a formidable problem. Formidable.
Thank you again. 10-minute coffee break.
High hydrogen loading of thin palladium wire through alkaline earth carbonate. Please.
Okay, my talk is a little bit different from usual work because we come back for the experiment starting mainly the loading with hydrogen. And when we move our experiment using deuterium in a specific electrolyte solution, we found the presence of some bacteria that has a quite deleterious effect about overloading. So my talk, I understand, is not so easy to be understood from the people, and for myself the same. So I try to make my best. It's a collaboration between physics, chemistry, biologists, doctors, so on. So according to our experience, 11 years experience, the cold fusion according to us is just overloading, really overloading of the palladium, and at the same time move deuterium inside palladium without losing of overloading. As people know, the main problem of experiments was the beginning, and now there are no possibility of the result. The typical VHS power, when we are lucky to get it, is about 5–10%. Sometimes, few times, I have to 200%, and even macroscopic value, and up to 100 of watts. So large value that to get completely sure was not a mistake of measurements or so on. It was true, but very, very hard to reproduce. I want to show for the several, always this our nice picture. This top experiment was done using palladium alloy with a 100 micron wire, filled with hydrogen lower and deuterium up. The difference is quite easy to detect. About why such as it. If we suppose there is some mistake in the measurements, so the hydrogen means 0, even 10% remain in deuterium. The other experiments make with pure palladium in center-wide geometry and pulse and electrodes and so on. We have input power about 50 watts, and we get an HS gain of up to 250%. This happens only during the loading. In a steady-state condition, nothing happens, even at quite large value. Only during the changing of the condition, not steady-state. So, because the problem of low reproducibility, we decided to study new techniques to get overloading. We decided to quit for this moment using deuterium and lithium. So we want to get a new procedure in order to get hydrogen body loading larger than 0.99. The time to get maximum should be not too long, less than 2 days, 50 hours. And the stability of overloading at least for 4 hours, in order to make some reliable measurement. And we want that the success rate of our procedure overall has to be larger than 60%. So what? Just remember the well-known Bernoulli curve, the deuterium and the hydrogen. Just remember it. We want to get at the minimum loading of larger content 0.95 or 0.97, because we have in mind the nice experiment graph of Cooper that show that when the loading is larger than 0.95, always it gets just hit. So our goal was to reach the Cooper graph of this area. So 0.95 in the deuterium means reagent ratio 1.6, and for the hydrogen 1.43. 43. This was our goal. The procedure is a little bit different from usual. We want to construct in situ like a diode using very thin amount of elements in order to improve the loading and decrease the bubble formation. Because recombination, and when it is done at enough large value, we will apply some electromigration in order to increase further the loading, but only when the loading is enough large, not before. This is a sketch of the apparatus, platinum anode, 30 centimeter long, palladium wire, 50 micron, and several pickup. And we try several electrolytes. We use a C method for fluorescence measurement. It's like a small history of our history about using new electrolyte. In '94, we just used 1 micron, palladium, and lithium. And we started to decrease the concentration from 0.1 molar up to 0.1 millimolar. And we have found some beneficial effect, but not stable. Side experiment using used lithium hydroxide, and we try a lot of different electrolyte. With lithium hydroxide, we use light water, so no problem about money for the deuterium. We are free to check everything. Later, we focalized our experiment using calcium and strontium, and with some addition of mercury chlorine. And this approach seems the good one. Loading hydrogen deuterium is not so easy. There are several problems. One is when the loading, the lattice is distorted up to 8% volume, there are superficial cracks that the hydrogen deuterium can escape. There are dislocation inside, internal vacancy. Moreover, this is some proof from people working at Tanaka and the NHL laboratory that very pure palladium, 9.9999, is not good for loading. So some impurity can help. Moreover, the metallurgical preparation and procedure for loading help for loading, like low high current procedure of Takahashi or partial electrolysis of our group, and so on. So, but all means not steady state condition. The procedure uses thin wire. Thin wire means small bubble diameter, so means large local pressure that can help in the way of gas. So there are, moreover, one point, large gradient of electric field inside the thin wire. This is one of the key points of the experiment. Large gradient of electric field, like in a proportional chamber for nuclear action. Moreover, we can change locally the range of the pH solution between 9 and 13, just changing the current density of the cell. And you make computer simulation about this aspect. So this procedure works when there are a little bit strange electrolyte solution, where we have a salt soluble in the electrolyte, but at the cathode, the salt change in another insoluble. So we use the side effect of carbon dioxide, always dissolved in the light of the heavy water, to make this trick. Moreover, if the thickness of the deposit is too large, the acidic solution dissolves the excess thickness. This computer simulation about the thickness of the coating, changing the amount of main elements deposited. All this done with the solution 1.3 liter 2 solution, wide diameter 50 micron, length 33 centimeters. And obviously the pH reached some steady condition after quite a short time, 50 seconds. So we have a mean pH of the order of 4.55, but locally about 10, 11. This is the same experiment using strontium, and strontium looks more easy to manage. Before it was done with calcium. Obviously, we try barium and magnesium, but the results are less good, so I will not show. This is one of the typical loading with hydrogen using calcium, and we have the wire set in two sections, up, down, and the final value are the final value of loading is quite good. Resistance ratio 1.4 for downside and 1.3 for the up. Our goal was to have resistance ratio less than 1.43, so we get the result in a quite short time, less than 1 day of working. Similar experiment made with strontium give even better result. In this experiment, the best resistance was 1.1. I think never you can watch in the literature this kind of loading in a stable condition. Another peculiarity of palladium hydrogen system is the changing of resistance of resistivity versus loading. This is the data from the literature. The resistance ratio, temperature coefficient of the resistance start from 4, reach 0.4, 0.1, and after they decrease at about 1.8 at the loading resistance ratio, loading 0.7. But no data available more for larger loading. We have done experiment with our overloaded palladium wire with hydrogen, and we found that this value increased again up to 3.3, and we started the system from liquid hydrogen temperature up to the boiling of the water. To make this experiment, we cover the palladium with a little bit thick amount of mercury in order to decrease the loading. This experiment was done without applying current, just keep wire coated with strontium, hydrogen inside, and some mercury outside, and after check. To be sure that the mercury don't make some strange effect and fake our data, we, after the experiment, we deload the electrolysis, the wire. This is the beginning effect of hydrogen deloading, mercury deloading, and after reach maximum later longer time, keep 1. So it means there are no error inside. Okay. okay, for this nice, happy condition, we want to move to heavy water. But there are problems. Our techniques works only with very, very pure light water or heavy water. So the impurity is a strong problem. The impurity are three kinds in organic conventional chemistry. Organic substance like carbon compounds and something living. I want to remember in our experiment we have 66 mole of light water. The amount in hydrochloric acid of some 10 to -5 mole, and the strontium to some 10 -5 mole. So means we add in the solution, in the 1 liter of solution, 1 milligram of strontium. 1 milligram, almost nothing. And the anti-cracking agent means the mercury is 10 times lower, 10 to -6. Really ultra pure water. So the impurity in the light water, in organic substance, in commercial, the United water, light water, are 10 milligram per liter. Distilled water, 0.3 milligram per liter. There are organic substance, but not so much, 0.2 milligram liter. And if you boil enough well, you don't have bacteria inside, or muff or other things. With deuterium, the situation is starting worst. Inorganic, 10-20 milligram, like United water. There are about 10 milligram of organic substance, called total organic compounds, and living things. So about the biological investigation was done to get close collaboration with Enea Casaccia, with the biologist group leader from Dr. D'Agostaro. And we have found a specific bacterium that change the pH of the solution from itself. Without current, you just put there, wait, the pH will change in the closed bottle. So it's not due to electrolysis problem, just a pH metabolites. One problem that seems is deposited on the surface of the cathode, so weakens the loading effect. And moreover, he likes as food the mercury. He likes sweet mercury, but we add mercury as anti-cracking agent. And he likes strontium, but we use it for loading. So it's a very strange animal. Just to remember the physical purity of high purity heavy water, extra grade. So the purity is very good, 99.92. But the permanent demand is quite large, 10 milligram per kilogram. Means in the closed bottle from the starting, just out of the company, there are several bacteria. Conductivity is very good, but easy to improve. In the pH, look, can be between 6 and 10. It's a strong proof. The heavy water, there are a lot of unknown materials that can make this large variation of the pH. The problem of organic compounds was detected in 1998 from a Japanese group, Sumi, Asami, Matsui, at NHA laboratory. But later they don't have enough time because they have to close the experiment, to go in the deep. But they have detected, they realize the total organic compounds can be a problem. So they were very clever, they don't have time only. So, experiment with pure virgin uranium oxide without filtering. the loading reached about resistance ratio 1.9. We add some mercury, the load improve, but after sometimes lose again to resistance ratio 1.8. Not enough for our purpose. We take some convection procedure, means loading, deloading, and so on. We have found the resistance ratio 1.82. We increase the current, the loading increase a little bit. The increasing current, the loading fall again. So nothing to do. We made another experiment using filtered deuterium oxide with 100 nanometers filters, very small size, a millibor in series. We have improved of the loading, 1.75, but even increasing current after there is no stability. But means the filter can help. Indication of something. This other experiment, it's the same before. We make a loading, the loading procedure, anodic, and so on, anodic stripping. We get some improvements. And the best result in this experiment was resistance ratio at 1.69 stable for 12 hours, but after again this deloading. But all our indication is something in the water that weakens our effort to load. So we developed a specific procedure, tentative